name is Blair Davis. I'm the Director of Decision Science at Cincinnati Children's. Again, ranked one of the best hospitals, so we're very excited about that. Let's see, I have the privilege today to introduce our first talk, Integrating Machine Learning Models in Insurance Analytics, a hybrid GLM-NLP approach. We have Dr. Nasser Mooman, Max Gruber, and Victor Adewapo from Great American Insurance Group. Dr. Nasser is a data science manager with a PhD in AI from the University of Waterloo, is a technology leader with 25 years of experience in academia and industry. Currently the data science manager at Great American Insurance Group, former CTO of Piriato Incorporated. Dr. Mooman has developed patent and FDA-approved biomedical technologies and AI solutions. Dr. Mooman's career spans faculty roles at Rochester Institute of Technology, co-founding tech startups and leading R&D teams for major corporations. Max is an associate actuary on the modeling team in predictive analytics at Great American. Is an actuary modeler on the causality claim model project and worked on both the GLM and NLP side. Victor is, Dr. Victor, sorry, I do see that now. Senior data scientist, holds a PhD and master's degree in information technology from right here in Cincinnati, University of Cincinnati, specializing in data science, AI, and computer vision. His research focuses on activity detection and incident prediction from video streams. He's received several awards, including the Data Science Fellowship from Lawrence Berkeley National Lab, Google Generation Scholarship, and the Young Alumni Award from the University of Cincinnati. Dr. Adewapo also serves as a technical reviewer for various academic journals and conferences. So welcome. Thank you.
Thanks. Good morning. Welcome to our Great American Insurance Group Data Scientist session. We have a set of sessions that we provided to the committee that include NLP with GLM, Vision AI, and multimodal generative AI. This one got high voted to be presented because it's the complexity of this particular approach. I think early this morning when we had the talk, the challenge is integrating generative or NLP into machine learning, GLM. So I think this particular approach that we have successfully deployed into our production since Great American Insurance Group are early adopter of AI and statistics within our environment. Just disclaimer, the data that we presented, illustrated in this particular slides, are fantastically driven, changed, altered, just make sure that we don't share each AI data, individual identified data sets. I will include my team, Max.
Thanks, Nasser. So to get started with our business problem, our goal was to identify potentially severe claims early in their life cycle. We can talk a little bit more later about the business value this drives, but the idea is to help devote our claims resources to claims that have potential for high severity and really need the attention. We score claims on a 0 to 10 scale. There was insurance software called Colossus that was popular in the early 2000s. You put in data and it would give you an exact dollar value of the claim. They got in legal trouble, media trouble. Our business partners said, please, we do not want Colossus. So we made a real effort to not do that. Plus our boss is here, so I want to make sure. And then model interpretability was a key requirement. We're regulated, we could be audited, and our end users really want to know how we're getting the scores. And structured data is limited. We have structured data on our claims, but the vast majority of the claim information is stored as text, and there's really not a lot there in our structured data. The types of claims we're focused on are commercial general liability and auto, specifically bodily injury claims and property claims. And a little bit of background on GLMs. So GLMs are Generalized Linear Models. It's probably the most common modeling technique in the insurance industry. There's a lot of reasons for that. They're interpretable. I could easily walk through a calculation with anyone and show how we get the score. We can explain it to a regulator. They have a lot of flexibility in handling distributions of data. Insurance data has a lot of unique characteristics. We don't get a lot of normally distributed data, and we can really handle that with the GLM. And then it's customizable because the calculations are straightforward and understandable. We can do whatever we want to with them. So a lot of times we'll make decisions or incorporate business knowledge within the model that would be much harder to do with something black box. And then really the last reason would just be that it's a known technique that's been around a long time. We have lots of employees familiar with them, regulators are familiar with them, so there's a big advantage to that familiarity. In terms of NLP, it was really a requirement for this project. So we have claims documents and claims notes. Adjusters, whenever they're working on a claim, are filling out claims notes. And so they have really thorough, rich descriptions of what's going on in the claim and the actions that are being taken. And this is not documented in structured data. So lots of key severity drivers such as facts of loss, correspondence with claimants, attorney communications, lawsuit information, and all sorts of other things is only available in the text. So the only real way to use this data would be with natural language processing. So the structure of our model is a GLM with really 3 different sets of data. We start with our internal structured data. So we have claim software that captures all the claim structured data. We have document systems where all the documents are stored and we can grab that metadata. And then we have claim note systems where we can grab metadata as well. And then we add on external structured data. So we purchase a lot of external data that we can use to supplement our models. And then we have our unstructured data. So our unstructured data here is really our claim notes. And we'll do a lot with that and then combine all of those features into a GLM that ultimately predicts severity. So our adjuster notes are really used for 3 things. Note metadata, string searches. I thought one of the really great points in the keynote this morning was about bringing NLP to machine learning and statistics projects, and I think a goal would be to use large language models to generate some of these features. There's only so much we could get deployed right away, so we're starting with string searches. An example, we have lots of key internal terms that our claims group uses. One would be like a flash notice, which is a report that we have on severe claims. And so we search for the terms flash notice within the notes. I think a better way would be to use an LLM to extract this information. We can't really tell if they said there's no flash notice or we wrote a flash notice, but it added value to the model and is where we're at right now. Nasser will talk a little bit more about where we can go in the future to incorporate LLMs to get better data there. And then we also have an NLP submodel that's built from the notes. And so I'm going to hand it over to Victor to talk about the NLP submodel.
Thank you, Max. So we have claim notes, like we have textual data, and we need to mine some of this textual data. We found out early on that our textual data contains wealth of information that it's not being used, and we could, generate insights from some of this text data, we could be able to model fraud or even identify risks from the text data. So we delve into using some of the natural language processing techniques to mine our textual data, which is typically unstructured data, right? So for the NLP submodel, we considered several techniques. I'll talk a little bit on the first two, then the last one, which is what we have currently implemented, I will delve deeper into that. So we tried some of the fine-tuned transformer model, like the bidirectional encoder representation from transformer, also known as BET model. We tried some of this LLM model that could be used for extracting or even mining text data to get some meaningful information, or even vectorizing this text data. We also played around with some of this neural network methods, such as the word-to-vec and glove embeddings, to be able to turn this text data into some sort of numerical features that could be fed into a machine learning model. Then finally, we tested also the TF-IDF embedding, which is just a time frequency inverse document frequency. Well, it seems TF-IDF seems to be the, if you're ranking in terms of technology and state of art, is the lowest in the group, but that performs better on our analysis. So we decided to implement TF-IDF embedding. I will talk about some of the reasonings behind going for TF-IDF down the line. So let's talk a little bit about what is a TF-IDF. It's just one of the oldest, way of embedding numerical or textual of embedding textual data, converting them to numbers or vectors, then feeding that into a machine learning model. So what is the full meaning of that? It's time frequency inverse document frequency. And it's kind of used to identify what are the important keywords in a textual data. And this method is typically useful when you just want to identify keywords. Like you don't really care about the order of events. Like you don't really care about continuous relationship about what happened 2 days ago versus what happened 3 days ago. It's typically useful to identify sensitive keywords that could be used to model risk. For example, if you had the word helicopter crash, it doesn't matter if in a claim life cycle, if the helicopter crash happened in the first day, or it was documented first day, or it was documented in X number of days. The fact remains that there was an helicopter crash, and that keyword is very important in the context for modeling. So I'll go into some example of what a TF-IDF look like. These are example text. We just made this up. The dog runs, the dog is black, the cat meows. And we want to be able to calculate the TF-IDF. I'll walk you through how to calculate TF-IDF, and you can leave after this presentation and tell your colleagues that you know how to calculate TF-IDF, and you can start doing some modeling. In this first sentence, we can calculate the TF-IDF for the keyword dog. Time frequency is just how many times did this word occur in a sentence. You have the keyword dog, it only appears once. And the first sentence has only 3 words. So that is, dog has 1 count out of 3 words. So if you look into that, you have the time frequency for the key term dog. Now, if you talk about the inverse document frequency, now there's a different way that different people implement the inverse document frequency. The SKLearn library has their own way. They kind of normalize to ensure that they don't have negative values. But in this simple explanation, I'm just using normal log. So we have the log, which takes how many sentences do we have together? We have 3 sentences. How many times did the keyword dog appears? It only appeared twice. So it kind of takes the count of that keyword in relation to all of the other documents you have. Contextualizing that, you have a lot of claims. You have several keywords. You want to see how important is this keyword in these thousands of claims that I have, in the book of business. So that is what the inverse document frequency gives to you. So when you multiply both of them, it kind of gives you an overall numerical representation of what is the true value, or what is the coefficient that should be assigned to this keyword based on your claim data set, or based on any text data that you use. This is applicable to any text data, not just claim. So we have the final value here, right? Then, just skipping all of those processes and repeating it for each keyword. This is what the final features is going to look like. So your feature is going to contain every single keyword that is in your text, right? And you could either have like a zero coefficient, or you could have some sort of numerical number that is normalized between 0 and 1, right? And this text data are then fed into like a regression model to calculate what is going to be the risk based on this keyword that are present in the text data. So you could see in this particular scenario here, I think one of the most important keywords here are like run, cat, and meal. Why? Because they only appeared once in the whole document, in the whole claims. And you know that this keyword are quite important. And this is an oversimplification of this process, right? We're just using 3 examples. But when you really get into like a big number of claims, think about it. We'll definitely get into that. So I don't need to get into that. So we chose TF-IDF because of the simplicity. You can see we all walk through how to calculate that. That's so simple, right? You can explain it to anybody. And we've tried other sophisticated method. You know, the keynote speaker earlier talked about some of these things are not interpretable. Why they are some values, we've also seen some value, we're using them in other use cases, but it's like you have to choose the right tool for the right task. Like you have a piece of cake, you will not take a chainsaw to like cut the piece of cake, you probably use of course, you don't get the work done, but you end up in more mess that you have to clean up than what you need to do. So, you know, simple thing that is precise, explainable is what we chose, and it kind of perform on the same level as other techniques. We're able to also customize this to our business specification because we're in the insurance domain. We have specific keyword, we have expert knowledge, we have domain knowledge of different people that understand some of this. So we're able to like incorporate some of those expert feedback into the modeling techniques, and I will explain some of those things. It's also very easy and very fast to compute, and again, it's natural for a regression task. So the NLP submodel itself, this is like the general overview of what we did. You know, just like let's say you have about 40,000 claims, and you vectorize and you walk through all those processes I just explained, you ended up with almost 1 million vectors. You know, think about it. You have 1 million features that you need to train the model. So we have the unigram. Unigram is like just using single word, like just a single word, dog, cat, meal. But when you talk about bigram, it talks about combination of 2 words like the dog. So you start creating more features and more complex relationship between the text data, not just a single word. You start trying to capture the relationship between each keyword, right? That is what one of the newer models, LLM, GPD, they kind of capture the contextual relationship, the order of word. Max was talking earlier about negation, not being able to identify if it says we don't have coverage versus we have coverage, or negation. So now capturing some of those complex relationship with bigram, unigram, and trigram. Then we fed all of this into the final regression model. I'm going to talk through the whole process lifecycle for the NLP submodel really quick. So you have claim node, you have a lot of nodes, 1 to n nodes, depending on whatever how this documented it is. For a single claim, you could have multiple or thousands of nodes. Then you process them, aggregate them, group them together. Then we do this life cycle that we have here, which is first thing is like pre-processing the data, tokenization, which are like standard processes when you start doing natural language processing and mining any text data. We have tokenization, just returning them to the string form. We have lemmatization, which is like, returning the word to the root form. So if you have the word running, ran, well, maybe that's a good example, rain, rainy, and rain. You want to reduce them to the root form, which is rain, right? So that's what lemmatization do. And the part of speech tagging help us to identify how do you lemmatize. So we did a lot of part of speech tagging for each keyword to understand is it an adverb, is it a noun. Now we'll do lemmatization on it. Name substitution, yes, that's where some of the domain knowledge comes in place, right? We have specific name, we have specific people that handle severity claim. We don't want the model to be biased or to overfit onto specific features. So we have to suppress some of those features. So we did substitution. We also did abbreviation. So, we all type, how you use short form. I think one of the few things we found out is when they want to leaving a voicemail, there are 17 different ways that we've seen that they reference voicemails. Some people just going to say VM. Somebody say VM. There are several ways for you. So we try to do some of this abbreviation. We remove stop words, and then we create a feature using the 10 frequency inverse document frequency approach that I explained earlier. This is fed into a regression model, and this regression model predicts a raw score, but in our use case, we are not really interested in predicting a dollar value. We wanted to be able to put it in 10 buckets and be able to rank, hey, this is what you should pay more attention to, and this is what you should pay less attention to. We do some calibration, then we have a final score, and that final score becomes a new feature that goes into the GLM model. And with this whole life cycle, we're able to implement some nuanced technique of natural language processing and embedding that with a GLM model. Now, this could go for like other use cases, like you have a LLM model or GPT. You could do all of this feature extraction or feature creation, then create like a table that's filled into a GLM. With that, we could explain the LLM submodel, you could explain the natural language piece, and you can explain the GLM piece. This is a sample output of what features may look like in the TF-IDF model or the NLP submodel that we create. You have some certain keywords. The red bar here actually represent those keywords that are going to increase the severity. The green represent those that may actually decrease the severity. Right here you see keyword like surgery, like acne, plema, like fracture, helicopter crash. They're going to definitely increase the severity because those keywords have significant weight when it comes to like our domain. Then when you have things like the dismiss, we don't have coverage, it kind of reduces the severity, and this is what it's going to look like if you want to explain some of the keyword or some of the feature that are in your text data to end user. And we even went further down to like explaining the text. And this is another sample visualization. These are not real data, none of this is real. So, just a reminder. So, you have a visualization that kind of identifies each keyword and kind of tells you, if you're a business manager, you're like one of the people at the helm of decision, right? You want to understand how did they arrive at this final value? What are the things that are driving this model? So we can tie all of those mathematical formula, those regression model back to a final kind of interface that people can kind of gain confidence. And the goal here is for people to support them in decision making. Like we're not just saying, hey, this is going to cost you X amount, and that's what you should pay. But we're saying this will help you to make better decision. If you see some keywords that doesn't align with what you think it should be, then you can kind of disagree and make your own decision as you mean. I'll pass it over to Max to continue for you. Thank you.
So the TF-IDF score becomes the most important feature in our GLM, and then we bring all of that data back to a GLM fit with the Tweety distribution. Insurance data people use Tweety all the time. There's a log link in the GLM that restricts your predictions to be positive. It handles the fact that we have a large mass of $0 claims, and it can accommodate heteroscedasticity. Our small claims generally are all have low variance, but when we get into really large claims, they can vary a lot. And so the GLM allows us to handle all of these things. So we have a lift chart here. It's deciled, so at the left end, decile 1, those are the claims we predict to be the least severe, and at the right end, decile 10 would be the claims predicted to be the most severe. And then the bars represent the relativities, so at decile 1, minus 90% would be those claims are 90% less severe than average, and at the right end, 400% would be those claims being 400% more severe than average. But you can see the progress we make as we add data. So we start with our internal structured data. We have decent lift, which is slightly improved, including our external data, but the NLP really makes a massive improvement. And the NLP, even on its own, is worth more than all of our structured data. So some pros and cons, some trade-offs for using a GLM compared to a different sort of machine learning model. The scores are interpretable and can be demonstrated. The data fits well in a Poisson Gamma Tweety model. claims have features. So if there's an auto accident, there might be 2 damaged cars and 3 people injured, which would be 5 features, and then that fits within the Poisson side of the model, and then each of those features would have their own severity, which gets the gamma side of the model. So we account for both of those factors, and then it's also customizable. So we can control for loss years. We customize for state relativities. There are states where losses tend to be higher, where we had minimal data, and we talked to experts from the field, claim professionals, to help us make those adjustments for states, even though we didn't have a lot of data to train on. And it's easy to make those adjustments in a GLM compared to something like XGBoost, where it's black box and you can't really get into the black box and make those adjustments manually. Some trade-offs: the GLM may be less accurate than an alternative technique, and it also is more difficult to fit. I think this is a little counterintuitive. People think that the newest machine learning would always be the most difficult to work with. But one of the nice things about something like XGBoost is that you just sort of put everything into the black box and then you get predictions out. And things like interactions, compound distributions, correlated variables, and all sorts of other issues that you manually have to take care of in a GLM are just automated in a machine learning model like that. And it may be better if you get to take care of those, but it also is a risk. If you don't handle them properly, you could run into problems that a machine learning model just wouldn't have run into. So our results, we have a lift chart here. We score claims from 0 to 10. Everything below a certain threshold gets a 0. And then we have even deciles, 1 to 10. And then to add differentiation to our most severe claims, we split 9 and 10 into 2 groups. So you can see that the holdout results, the claims that are predicted to be more severe, really do have a lot higher severity on average. And then we walk through sort of some different structures. So if we start with just our structured data, like that decile 10, those losses are 315% compared to average. They're like 3 times worse than average. The TF-IDF model alone has more predictive power than all of our structured data, but combining those 2 things really gives our best result. And we also have an XGBoost model here compared to the GLM, and by our evaluation metrics, it's comparable. And so we really felt like the GLM is the better option if those 2 things are comparable because of the reasons mentioned earlier. So on our holdout set of high severity claims, our claim professionals have large reserves on them, 46% of them at day 90. So they generally do identify them, but the reserves aren't always up to where they need to be by 90 days. The model scores 86% of these claims that end up being large as 9s or 10s by day 90, and then combining either the high reserve by the adjuster or the model, we can catch 93% of claims that end up being high severity by day 90. So that is really the idea here. Can we catch more of these potentially severe claims early on? And so, yeah, our goal is not to make precise severity predictions, but we think we can add a lot of efficiency to our claims handling process. So one way would be triage. We would put more experienced adjusters on potentially severe claims right away, and get this experienced adjuster there immediately instead of waiting for things to develop poorly and then changing adjusters on a claimant later in the claims life cycle. Claim elevation. So we have quarterly claim evaluations with claims leaders. We think this model and the scores can generate good claims for them to look at and review. And they don't just have to look at claims with high reserves. They can catch claims that will end up being severe before a high reserve is posted on them. Reserve reviews, we track claims with low reserves but high claim scores. And so claims managers can come in and see all of the claims that come up through their reporting structure that have high scores but low reserves, and check the reserves on those claims to make sure that they are sufficient. And then attorney selection. We want to make sure we have the right attorneys on the right claims, and so allowing our claims leaders to see the claims that are potentially severe early on should help make sure that those claims have the right attention on them. So I'm going to give it over to Nasser to talk about incorporating LLMs into this.
Thank you, Max. So if it works, why we have to change it? Of course, so we have to make it better, of course, right? So we solved two complex issues. One, integrating NLP, which would be generative AI, into a GLM. Second, you have to make sure the results of the model is interpretable. So GLM is very easy to interpret data. How could we integrate GLM or LLM into the GLM without losing the core feature, which is interpret the results? So we solved this complex problem. And then secondly is, what we could say actually is more into the scope of customizable. We have many use cases. So I think TF-IDF is a very ideal tool that can be customized for this particular data set. However, we do see the advantage of applying generative AI into two scope of really the GLM within and outside. So within, we could, for example, look at unstructured data, extract such features, and then add those features as part of structured data. We could summarize some data, and we could extract some other features using name definition, some other tools. And then the other scope of it, actually, we've got external piece, which is mining claim document, which is beyond claims, for example, right? So what else we could do? You could compare, find similarity between claims. You could classify claims. So since we have a lot of other use cases, I think some of those particular models can be adapted to generative AI, where we could utilize either within enhancing the actual GLM model, or from outside where we could make the GLM or the model more accurate. I think we conclude our talk. We are open for any questions, suggestions, feedback, but I think the complexity I could summarize in two things: integrating NLP with machine learning model. I think we heard this morning the challenge. I think our team has successfully conquered that particular challenge. LLM will be much easier now to integrate that without compromising the interpretation of the results. And from the American Insurance Group, we already apply generative AI, GLM, and different other applications, but we have to go more guide rail when we're going to use it to avoid we call hallucinations as well as drifting of the model. When we apply a model to any particular use case, we want to make sure this model is to enhance our underwriters and agent life, making our life easy. At the same time, we are really accountable for what model we presented, what accuracy, what metric that we presented to the end user. Thank you. We're over for questions now.
So for this model specifically, what were some of the unforeseen challenges that were observed in development or through the implementation of this GLM-NLP approach?
I think one would be data. So we tried to work with business units that are in our current claim center where all their data is structured. But when we got into claims that are a little bit older, we all of a sudden had to pull notes out of legacy systems. That was a big task. We had to bring in people from IT who knew the legacy systems. You had to export gigantic files and move them through the firewalls and secured storage. And so the quality on the old data was bad. We found we had these claims where it said 700 notes were written on the same day in 2009, and that's not accurate. And so dealing with data quality issues, especially on older data, before we were on our current systems was definitely a challenge. And I think going forward, when we have more data on our new systems, it'll be easier to retrain this and improve and get more high quality data to work with.
Thank you.
Yes.
So this may not be a fully formed thought, so apologize. But you mentioned that you're using this, one possible application for this is to triage and shift to more experienced adjusters. I assume the data is trained on fully closed claims. And so like I was just curious to like the level of performance sort of like as the claim comes in early in its life cycle, how well the sort of initial notes are predicting, like how has that work, like you see the so like if it's trained on the fully fully closed claim, you have a whole series of notes where experienced adjusters may have been brought in and you get some more data. But if your early one currently on a new claim is an experienced adjuster who's not putting those keywords in, like does that, like did you account for that? Is that in there somewhere? I was just curious with the triage application in particular.
So that is a great question and definitely something that has been talked about a lot. So we've tested training, well, we use closed claims, but like cutting off the notes at, say, if we're scoring at 3 months, then we will only use the first 3 months of notes in training the model, and then use a model that has those 3 months of data, and we found generally that we get good performance on training notes with the time frame that we're doing the scoring with. So in that case, like we've tried to adjust and test scoring at different time frames. We definitely get better predictions as more narrow notes are written into the claim. We've tried scoring very early, and like the more information, obviously, the better. I think there still is going to be an issue always, like if there are no quality notes written in the claim, we don't get anything. But generally, all of our adjusters are pretty well trained to write decent notes. And if you can get some basic details about even just the facts of loss early on, the most severe claims have much worse facts of loss. And so without having the most thorough data, we can still make predictions that are pretty good and useful. And I think that's really also an area where if we can extract more features and make the model better, getting earlier, higher quality scores would add a lot of value.